All right, this is page 9 of the computer system notes, and it is section 6, virtual memory. And there's a text reference for it, although it doesn't have a lot of detail in it. So virtual memory, again, this is of interest to those people that like the systems programming type jobs, and it's definitely a good thing to be aware of. Every general purpose operating system uses virtual memory, so Mac OS, Windows, Linux, and so on. It is confusing, I'll warn you up front, so it's kind of eating your vegetables here. Okay, so just to start off with, so in a general multi-processing operating system, every time you start a new program, you started a process. So the thing that's running, that's executing your program, that's a process. So each process has a virtual address space, and virtual is the key word there. So it's kind of an imaginary address space. So it fetches instructions from virtual addresses, it gets data from virtual addresses, and these have to be translated to real locations in the physical memory in your RAM. And so I'm going to draw a diagram to try and show you what's going on here. So over on the left, leave a little bit of room on to the left of this for some labels. So this is process 0 over here, and process 1 on the right. Again, leave a little bit of room to the right of it. And I'm going to use 8 lines here. Hopefully that was 8. And just going to make looks like an array. So that was 8 lines, got that right. And this represents the address space for process 0. So it's all the addresses in memory that it can generate. So up at the top, I'm going to start with address 0. So this is a hexadecimal address. I should have prefaced that with a 0x. And that is, if you're using 32 bits, you'll use 8 hexadecimal digits. And that's the lowest address that you can generate, 0. And the highest address, what do you think that is? So 32 bits, they would all be 1s. If you're converting 4 1s from binary, that's 15. In hexadecimal, that is F. That's the highest hexadecimal digit. So that is the largest address that can be generated. So the addresses are going to be in that range. And now the address range is divided into something called pages. And so this is going to be virtual page 0, virtual page 1, virtual page 2, and so on, up to virtual page, let's say n-1, where we've got n virtual pages. So these are, so the address space is divided into pages or virtual pages. And the size of those, they're bigger than your cache line size. So cache line size typically is maybe 64 bytes. A virtual page size has traditionally been about 4 kilobytes or kibibytes. And the reason for that is that sometimes these addresses, sometimes you have to move virtual pages from main memory to the hard disk, and so you want to move larger chunks of data. Otherwise, you get hit by the, oops, didn't want to do that, I want blue. You get hit by the latency penalty of the hard disk. Okay, so process 1 also has its own virtual address space. What this means is that each process thinks that it can see from address 0 to whatever the highest address is of the main memory, but they are actually referring to different memory locations. So there, that's process 1, and it's going to have its own virtual pages. So virtual page 0, virtual page 1, virtual page 2, up to virtual page n-1. Now, these are imaginary, and so we have a real memory sitting here, and I'm going to draw it with 4 lines. So this is the main memory, and let's just say that the amount of physical RAM that we have is half of the address range. So that would be 7FFF. Whoops, that's pretty tiny. Anyway, so with 32 bits, you can address 4 gigabytes or gigabytes. And so main memory, let's just say we got 2 gigabytes of main memory. And I'm going to number, it's also divided into pages, and I'll number them 0, 1, 2, and 3. These, for some reason lost in time, these are called page frames, but they're pages in the real memory. And it's just a logical subdivision of main memory. So what happens is when a process gets loaded, let's say that process 0 got loaded first, and it was the first one running, and so its first virtual page got allocated a page in memory, and let's just say it got allocated the first page in memory. And let's just say that's where, it's the code for the program lives, and the stack lives at high memory addresses. So the stack is going to be down at the bottom here, and let's just say that that last page has been mapped to page 2 in the main memory, and it hasn't actually used any of the other pages, virtual page 1, 2, and so on, yet. And then over here in process 1, the first page, typically that's going to have your program text, the instructions. Let's say that it got assigned page 1 for whatever reason. So this is all just hypothetical. And say its stack, which is at the bottom, got page 3 in main memory. So the pages in main memory are managed by the operating system, and they're just allocated on a demand basis. Now, what if, say, process 1 wants to use virtual page 1, so its program text is bigger? Well, the operating system would have to make room in the main memory because it's filled right now with those 2 pages from each of those processes. So it would have to swap one of the pages from main memory out to the hard disk. So let's draw the hard disk down here. So kind of like a tuna can, I guess. This is the hard disk drive. And so maybe if process 1 is running, process 0 has been idle for a while, and process 1 wants to allocate virtual page 1. It needs more space. So maybe process 0's first page there, it hasn't been used for a long time. So it gets swapped out to the hard disk. And so that's kind of weird. Its memory is living on the hard disk. What happens is if process 0, next time it runs, maybe it's asleep right now waiting for a timer or some I/O. Next time it runs and it wants the data that's in its virtual page 0, the operating system is going to have to make room for it in the main memory, so it's going to have to swap something else out. But anyway, we've moved that page, so now we can put process 1's virtual page into that first location. So this is all kind of weird and complicated, but it works. And so virtual memory was introduced quite a while ago when memory was expensive. So probably, I would guess, I can't remember, but early 80s, something like that. And so it would allow your processes to think that they had more memory, to work with more memory than you actually had RAM. And you could just swap parts of your main memory out to the hard disk and then bring them back when they were needed later. It's kind of slow. And so back in the days of like Windows 3.1, for example, you might see your hard disk light flashing a lot when you switch to a different program. I shouldn't say Windows 3.1. I don't think it had virtual memory. But whatever came after that, I can't remember now, XP or something. So you would see your hard disk light flashing a lot, and it would be swapping pages to and from the hard disk. Nowadays, we've got, RAM is relatively cheap, and so usually you can fit most of your running data into the hard drive, into your RAM, so you don't see that swapping happen as much. So the benefits are that it increases the available memory by swapping to hard disk. First computer I bought, if I remember right, it had 12 megabytes of RAM, and that was actually an upgrade. I think the default for that laptop was 4 megabytes. So yeah, and the other real benefit that we get from it is that the virtual processes, their access to the main memory is controlled by the operating system and the computer hardware, so that process 0, for example, can't accidentally or maliciously access the memory belonging to process 1, because it will generate an address and it will be mapped to a location in its address space. There isn't a way for it to access process 1's. So it gives protection between processes, so they can't modify each other's memory or read each other's memory. So think about, you're running an application on a server with other users in that server that you don't know, can't necessarily trust them, so that's a good thing. Okay, and so the page size is large, that's compared to cache line sizes. So, for example, 4 kilobytes has been a standard page size for quite a while. It's to take advantage of the hard drive's bandwidth, but to also overcome its latency or to hide its latency. So I'll just say to take advantage of hard disk drives, not latency, bandwidth, and to overcome the latency, so we'll say and overcome the latency.